Okay, this teeny tiny little video, or hopefully it's a short video, really isn't something that is so much a topic in your book as a helper topic, and specifically it's dealing with calculating areas of triangles, specifically triangles that share certain properties. Okay, so in terms of where we're located in the book, this would be located when we are dealing with area, and specifically it's at the middle to end of section 23, right after we got the formula for the area of the triangle. And I went ahead and in that paragraph that you can see at the, I guess, sort of middle of the screen right here, I went ahead and wrote in theorem 23.2, which is the theorem that at the very end here gives us exactly the standard area formula for area of a triangle that says, hey, if you want the area of a triangle, it is simply 1/2 of the length of the base of the triangle times the length of the height of the triangle. Okay, so that's exactly what we're going to use for this entire time. Now, I've got a couple different examples of triangles, and I didn't do anything special when I prepped out these triangles. I just literally took a stock triangle and put in a couple of lines. So suppose you have this triangle right here, and let's go ahead and name it so we can reference it in the future. So maybe this vertex down at the bottom is A, maybe the one at the top is B, and maybe the other one for the big triangle is C. And notice you've got that line right here dropping down from B to AC, so maybe that's at point D. Now, let's do a couple of things, and I'm going to go ahead and not use a standard notation right now. I'm going to use the horrible notation of X. And let's go ahead and assume that line segment AD and DC are in fact congruent to each other, which means the length of the line segment AD would be, pick your favorite letter to represent that length. Normally or standardly, you would say B. I used an X. Let's be good in the next examples. I'll leave it as X right now since I just put that in. Okay. Now, suppose we want to compare. So the idea here is we would like to compare or relate the area of the triangle ABC, so that's the big triangle, with the area of the two smaller triangles formed. So this would be the area of ABD and the area of the one that doesn't include A. So how about BCD? Okay, so that's what we would like to do. Now, if we look at each one of these three triangles, for all of them, if we want to calculate the area, it's going to be the formula 1/2 base times height. So for all three of these triangles, all three of them actually lie on one line, the line AC. So I'm going to let the line AC represent the base for everybody. And let me go ahead and highlight that just so we remember that throughout this example. That guy is going to be the base for all three of our triangles. Now, obviously, for the two little triangles, you're not going to include the entirety of AC for the base. You'll only take the part of AC that's actually one of the sides of the triangles. Now, what can we do? We can go ahead then and compute the height and the base for everybody. So for the big triangle, the base of the big triangle would in fact be, and let me go ahead and use the symbol B since we haven't used the lowercase b here yet. This base would in fact be 2x. Okay. The height of this triangle. Now, since we didn't actually form the height, well, actually we can. The height here is simply going to be an altitude. And in this particular case, I'm going to go ahead and, because this triangle turned out to be isosceles originally, I'm just going to go ahead and say, hey, you know what, BD turned out to be an altitude, and I'm just going to call the length of BD H. So over here, when we look at the height, I'll just say the height here is H. Okay. Now, put that all together. This tells us that the area of triangle ABC is exactly the same as 1/2 times 2x times h. In other words, x times h. Now, if we look at the second triangle, the triangle ABD, so that's the triangle on the left, the little triangle on the left, the base is not going to be the full line segment AC, it's only going to be A to D, so our base here is simply X. Notice, however, the height is exactly the same. If you share a base and you share a third side, in this case the point B, your height stays the same. And here we'll get that the area of the triangle ABD is exactly the same as 1/2 times x times h, and I definitely did not need parentheses. Notice the relationship here. You have that the base of this triangle was half the base of the previous triangle. Notice then, what did we get? We got that the area was also half the area of the previous triangle. This is not a coincidence. If we look at the last triangle, this would be the small triangle on the right hand side. Here we'll actually get the exact same base, x. We'll get the exact same height, and I'll still call it h. So this tells us that the area of triangle BCD would be 1/2 x times h. And notice in this particular case what happened. The line segment BD in fact split the triangle ABC in half with respect to area. Okay. Now, what did we just say here? We said that the relationship of the base of these three triangles, which shared a third vertex, the relationship of that base actually corresponded exactly to the relationship of the area of the triangles. Now, let's see if that holds on this next example. So for this guy, let me go ahead and label the top vertex as A, then B and C, which means in terms of the bottom here, we're going to call this bottom BC would be labeled with lowercase a, and let's actually meet standard conventions here. In this case, I'm going to go ahead and assume that the point D actually lies 1/3 of the way along the line CB, 1/3 away from point C. So here, I'm going to go ahead and label CD with an A and BD with a 2A. Notice that means as you're walking through that line segment C to B, when you get to the 1/3 point, you've got to D, and then you go 2/3 more. Okay, so what this tells us is that in total, this side BC has a length of 3A, and that just allows us not to deal with fractions. Now we can do the exact same thing that we did in the previous example. If we go ahead and look at our three triangles, so triangle A, B, C. In this particular case, we can look at the base, and I'm just going to label B for our base. Our base here, well, let's figure out who we want to be our base. If we are going to compare the triangles ABC with the two smaller triangles formed, we'll want the triangle ACD, and we'll also want to look at the triangle ABD. Now, when we compare these three triangles, we notice that if you look at the line segment BC, all three of those triangles have a side that at least lies on part of that line segment, which means the common or shared base that we want to grab right here is going to be that line segment BC, or at least some part of it. All three triangles then share a common third vertex, which is the vertex A. This is super duper important. Okay? What that means is the height for everybody is simply going to be h, if you have that criteria. Now, the bases will be different. So in the large triangle ABC, the base is going to be from B to C. So this means we have a total of 3A for our base. If we look at the triangle ACD, the one on the left, in that case, the base is simply CD, or if we look at it in terms of length, the length here is simply A. And if we look at the base of the last triangle, the triangle on the right, ABD, its base is B to D, or it has a length of 2A. Now, put this all together, and we'll get that the area of the triangle ABC, the big triangle, is simply 1/2 times 3A times h. And if we go ahead and simplify that, that's simply 3 divided by 2AH. Now, we can also go ahead and calculate what? We can go ahead and calculate the area of the triangle ACD. So this is the triangle that is on the left. And this area would be 1/2 base, which is A, times the height, which is h. And if we then go ahead and finish off to find the area of the last triangle, the triangle ABD, the triangle on the right, we'll go ahead and have 1/2 base, which is 2A, times height. This one simplifies to simply AH. Okay. Now, notice the relationship here. If we look at the bases, the base of triangle ACD is 1/3 the length of the base B to C, the length of the base of the big triangle. So I'm going to claim the following. I'm going to claim that the area of triangle ACD is exactly 1/3, or how much of the big base of triangle ABC, 1/3 of the area of triangle ABC. Now let's see if that actually works. So here's where I'm going to go ahead and do a little bit of scratch work. I'm going to tuck it in there because, well, I didn't leave enough space when I prepped out where the triangles were. So here we have 1/3 times 3/2 AH, and notice we can cancel out the 2 3's and we'll get exactly the 1/2 AH that we started with. I'm also going to go ahead and claim the same thing works with our last triangle, triangle ABD. In this case, the base of triangle ABD was 2A. 2A here is 2/3 of the entire line segment BC. So this is supposed to be 2/3 of the area of ABC. Now, if we have 2/3 multiplied by that area, the area of ABC was 3/2 AH. And in this case, those two fractions totally cancel. And we will get exactly the area that we are supposed to be getting. Okay, so notice correlative here, you totally have that if you set this up where you have one line that's where all 3 of the bases live, and the third vertex of all of the triangles is shared, you'll get this sort of relation. And last deal right here. Last deal, go ahead and put in some naming conventions. Point A, point B, point D, point C. And in this particular case, if we go ahead and label these, I may go ahead and say that this looks like maybe 1/4. It's roughly 1/4. So I'll call this guy A, and then 3A. Notice with doing little work whatsoever, I am going to claim the following. I'm going to go ahead and claim that we can say that the area of triangle ABD is what? It's 1A over the total B to C. So let me go ahead and highlight our shared base. Okay. 1A over 4A. Whoa, do not do that. 1A over 4A times the area of triangle ABC. Notice that is exactly the same thing as saying 1/4 times the area of triangle ABC. If you want to do it where you have this fraction of the actual length of the line segments, the A's in this case would always cancel. You can do the exact same thing if you wanted to find the area of angle ACD. In that case, though, if we set this up, it would be 3A over 4A times the area of triangle ABC. And notice here, this would of course simplify to 3/4 times the area of triangle ABC. And notice you must have what? The area of those two smaller triangles must actually sum up to the area of the large triangle. And notice 1/4 the area of the large triangle plus 3/4 the area of the large triangle, of course, sums up to your large triangle. Okay, so that's a crash course in what happens if you want to look at parts of a triangle.